almost 14 billion years ago, to be precise 13.8 billion years ago, the universe was born in a hot Big Bang. Since then, that's how we've known it. Space has expanded with time, and matter has undergone gravitational attraction. However, there's a limit to everything we see. At a certain distance, galaxies disappear, stars fade, and no signals from the distant universe can be observed. Why is this beautiful distant unknown so alluring? Scientists are plagued by questions. If we assume the universe is limited in volume, does it have boundaries? Can we reach them? What does the edge of the universe look like? The legacy of Hubble and the need for Webb. Orbital telescopes will always be at the forefront of cosmic discovery. They are unhindered by Earth's atmosphere with its distortions and cloud cover, nor by the vibration and noise on the planet's surface. Since the Hubble Space Telescope was launched into low Earth orbit in April 1990, the world has been amazed by many incredible discoveries. Thanks to this device, detailed images of distant nebulae and galaxies, even those invisible to the human eye in the night sky, have been obtained. One could say that Hubble is still quite capable of its tasks, but we always want more, don't we? It's time to open a new era in space exploration. 20 years ago, scientists began assembling the next-generation telescope. This future conqueror of space is named after the famous NASA administrator of the 1960s, James Webb. Why are all space enthusiasts so eagerly awaiting its launch? Webb's unparalleled capabilities. The James Webb Space Telescope, JWST, which will soon replace its colleague Hubble in orbit, is designed to push the visible boundaries of the universe even further. Stars and galaxies emit light that travels for millions and even billions of years. Along the way, it undergoes significant changes. For example, dust clouds can completely absorb all visible light from a star. In addition, the expansion of the universe leads to the redshift of light, so light waves become longer, shifting their range towards red, or even invisible infrared. To detect the most distant galaxies, highly sensitive instruments are required. Studying planets is also no easy task. They don't emit light. They only reflect the rays of their stars. But what if a star's rays weaken even before reaching a planet and are completely invisible at greater distances? The only reliable way to observe exoplanets is to monitor their own thermal radiation or how they transit their stars. And here again, a highly sensitive instrument is needed. The average temperature of most planetary bodies rarely exceeds 0 ring operator C, and often drops far below -100 ring operator C. However, Earth's average temperature is about 8 ring operator C. Just imagine how many relatively close planets remain invisible, and many of them could easily be habitable. Webb's design and operation. The James Webb Space Telescope is designed to answer these and even more global questions. Its instruments are optimized for the deepest infrared spectrum of light, allowing it to see very cold objects and peer through dust clouds. Within the solar system, it will be able to detect a body with a temperature of around -170 ring operator C, and for stars within a 15 light-year radius, it could detect a planet with Earth's or Mars' temperature. James Webb will be able to detect planets, as well as their potential moons. By looking at the infrared light emitted by all objects in space, the telescope will see stars that are too distant for Hubble. 18 large hexagonal mirrors, made of lightweight beryllium and coated with gold, will collect infrared readings for the orbital station. They will operate at temperatures near absolute zero at the Lagrange Point L2, which is located just beyond Earth when viewed from the Sun. Webb looks like a diamond-shaped raft equipped with a thick, curved mast and a sail. The raft, with its underside facing the sun, consists of a shield, layers of captains separated by vacuum gaps. This is for effective cooling, and together they protect the primary reflector and instruments. Captain is a very thin, human hair-like polymer film. It can maintain stable mechanical properties under extreme heat and vibration. For example, you could boil water on one side of the shield and keep nitrogen liquid on the other. Crucially for launch, Captain folds excellently. A structure resembling a ship's keel protects the sunshield and solar panels that power the spacecraft. In the middle is a box containing all the vital support functions that make Webb work. Externally, an antenna rises from this box, helping ensure everything is oriented correctly. At one end of the heat shield, perpendicular to it, is a momentum trim tab. It compensates for the pressure exerted by photons on the spacecraft. On the space-facing side of the shield is the sail, Webb's giant mirror, part of the optical equipment, and an equipment box. The 18 hexagonal beryllium segments will unfurl after launch to form one large, 6.5-meter primary mirror. For precise focusing, the main mirror's mounts cannot shift by more than 38 nanometers. This is a very precise system. Everything must be simply perfect. After the secondary mirror was installed, the telescope has been undergoing tempering in a cryogenic chamber for over a year. These tests check the reliability and correct operation of all its systems under conditions close to real ones. Next, the telescope will undergo new tests, where all its functions will be checked entirely. Pre-launch testing and future missions. Upon completion of cryogenic testing, the optics and scientific instruments of the James Webb Telescope will be integrated with the spacecraft elements, the Sunshield and the bus. After that, all elements will be assembled to become the complete orbital space observatory named after James Webb. It will then again go through a series of tests and launch simulations. Despite its size, with a total area of 25 square meters, Webb's launch weight is relatively light, 6.5 tons. Hubble weighs a full 11 tons, despite being much smaller. After all checks on the spacecraft are completed, there will be the launch and the beginning of a new chapter in astronautics. The telescope will undergo a 6-month commissioning period and will operate for 5 to 10 years, or perhaps even longer depending on fuel consumption. The distance from the telescope to Earth will vary. At its closest point, Webb will approach Earth at 374,000 kilometers, 10,000 kilometers closer than the Moon. At its maximum, the telescope will move away by 1.5 million kilometers. The challenges of remote operation. However, such a distance also has its drawbacks. After the telescope is launched into orbit, it cannot be improved, repaired, or modified. There are no active technologies that could deliver a repair crew to it. Hubble was a bit lucky in this regard. Over 27 years, a repair crew repeatedly visited it. Sometimes vital elements failed, sometimes new equipment needed to be delivered, and there were even force majeure events such as Earth's magnetic field anomaly, which caused the telescope to regularly shut down. Webb can expect no help. That's why testing and all sorts of checks are happening now, which has repeatedly postponed its launch. By the way, while all this fuss and checks around Webb are ongoing, scientists have extended Hubble's mission. It will now continue to delight us with discoveries until 2021. Webb was originally planned to launch in 2014, but significant delays forced NASA to move the estimated mission start date to September 2015. Then, the same problems forced a postponement to October 2018. And now they say the telescope will be launched between March and June 2019. Well, we'll wait. Webb's first targets. Meanwhile, time on the Webb telescope is being actively allocated. I think it's almost coming to blows. Telescope observation time is allocated to scientific teams based on competitive applications. It is already known what Webb's first targets will be. Observations of Ceres, Pallas, Exoplanet HD 189733b, with supersonic winds, HAT P26b, which has water, TRAPPIST 1e, located in the habitable zone of a recently discovered 7-exoplanet system, and many others. Among other objects on the priority research lists are the well-known Beta Pictoris system with its debris disk, the Horsehead Nebula, the supernova remnant SN 1987A, and several quasars that we see as they were a billion years after the Big Bang or less. Imagine the new and exciting discoveries that await us. It's breathtaking. We also have a lot of interesting content coming up on our channel, so don't forget to click the bell icon under this video. It will notify you when our new video is released, and then you'll be among the first to watch it. See you soon.